What's going on, guys? In this video we're going to do a review of linear regression in KNN. It won't include any of the math, it's just going to be about the main ideas. Okay. In section 2.1 we learned how to estimate our coefficient estimates. We then learned that we can interpret our model as with a 1 unit increase in x1 we can expect a beta 1 unit increase in y. And then after we estimate our coefficients we learned that we can make predictions from our coefficients. If we take the actual values of our observations, or observed, and then minus our predicted value, we're going to get residuals. Now the parameter estimates we choose is going to minimize the sum of square errors, or the sum of our square residual values. And by doing this, the sum of our error values is going to equal to 0. Now the 3 test statistics we learned are the SSE, SSR, and SST. So SSE is the unexplained variability from our model. SSR is the explained variability. And SST is the total variability. So the total variability is going to be equal to the unexplained variability plus the explained variability. And this is also known as the residual sum of squares. And this is the sum of squares regression and sum of squares total. We then learned we can quantify the performance of our model using the residual standard error, which is just equal to the square root of our mean squared error. And the residual standard error can be interpreted as the average amount that the response will deviate from the true regression line. Or we can use R squared, which is just the amount of variability, or I should say percentage of variability, explained by our model. So our goal is to minimize the residual standard error and is to increase the value of R squared. In 2-2 we learned the statistical tests for simple linear regression. So we could find if a parameter estimate is statistically significant by using a null hypothesis that our parameter is equal to 0, or alternative hypothesis that our parameter estimate is not equal to 0. Now, if our beta 1 estimate is not statistically significant, and this is evidence to drop that parameter, and then if our beta 0 is not statistically significant, you still generally keep it in the model or it will bias your results. We also learned that we can use confidence intervals to see if our coefficient estimates are statistically significant. So if our confidence interval contains the value of 0, so here it does not, so we can say it's statistically significant. If instead our interval was -5 to 5, since it contains the value 0, we can say it's not statistically significant. So this would be evidence to drop that predictor. And then the third way to check if a predictor is statistically significant is we can use p-values. So I don't think we covered this in the video, but essentially this is R and R output. So if we were to run a linear regression model, this is what our output would look like. So we have one predictor, x, and so this would be the coefficient estimate, its standard error, its t-value, and then its p-value. So that for the p-value, if it's below our significance level, so say we're using 95% level of significance, since it's less than 0.05, we can say that our x predictor is statistically significant. Now if we were to look at our intercept term, so it gives an estimate of 0.45, standard error of 1.08, a t-value 0.414, and the p-value is 0.7068. So we would say that our intercept term, or beta 0, is not statistically significant. So those are 3 ways to check if a predictor is statistically significant. Then we can also form confidence and prediction intervals for our predicted values. So a confidence interval is the range of the mean responses. It's a confidence interval. And then a prediction interval is the range of a single response. So confidence interval is always going to be narrower than our prediction interval. So this could be our confidence interval. And this will be our prediction interval. So the narrowest points of both the confidence and prediction interval are at the mean of our independent variable, or x bar. And this also applies when we add more predictors. So say we had y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. So the narrowest point of our confidence and prediction intervals would be when x1 is equal to its mean and when x2 is equal to its mean. In 3-1, we learned that we can add more than one predictor, and this gives us the ability to add categorical predictors. So when we add categorical predictors, we end up with an extra k-1 coefficient estimates, which here is going to be beta 2 mild and beta 3 high. And then the other level or class is going to be added to our intercept, which here is just cold. Now our beta 2 coefficient estimate can be interpreted as the difference in the mean between cold and mild. And our beta 3 coefficient can be interpreted as the difference between the average of cold and hot. We can also add interaction effects. So with an interaction effect, here we have 2 variables, x1, x2, and now we're making a new variable, x1 times x2. So our beta 3 coefficient can be interpreted as, with a 1 unit increase in x1, we can expect a beta 3 unit increase in x2. Or, with a 1 unit increase in x2, we can expect a beta 3 unit increase in x1. And then finally, we can add polynomial terms. So with a polynomial term, now the interpretation changes based on the value. So here, for instance, if our x1 value is greater than 1, then it's going to have a decrease in effect on our dependent variable. If our x1 is less than 1, then it's going to have an increase in effect on our dependent variable. And then if our x1 is equal to 0, it's going to have no effect on our dependent variable. So the effect that it has on the dependent variable is going to change based on what value it takes. In 3-2, we learned how to do the statistical test of multiple linear regression. So if we were to take a t-test of our beta 2 parameter, our null hypothesis is going to be that our beta 2 parameter is equal to 0, and our alternative hypothesis that our beta 2 is not equal to 0. So what this is saying is that if we fail to reject, then saying the mean between mild and we said is cold is the same. And if we reject our null hypothesis, it's saying that the mean between cold and mild is different. Now, if we want to see if any of our predictors were statistically significant, we would use an f-test. So with an f-test, we're saying our null hypothesis is that beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. And then our alternative hypothesis is at least one of beta 1, beta 2, beta 3 is not 0. So with the f-test, we check in if any of them are statistically significant. Then we can do a partial f-test, say if we wanted to see if cold, mild, or hot was statistically significant. In which case we would do beta 2 is equal to 0, and beta 3 is equal to 0 will be our null hypothesis. And our alternative hypothesis would be at least 1 of beta 2 or beta 3 is not 0. So if you fail to reject or you get the null hypothesis, then you can say that the means of mild, hot, and cold are the same. And then if you do reject, you can say at least one of them is different, in which case you would keep all 3 in the model. And then we also learned about the hierarchical principle. So what the hierarchical principle says is that if you have an interaction effect or a polynomial term, this could be x1 times x2 instead, if you're found that this term is statistically significant, you want to keep the lower orders in the model. So if the x1 squared or beta 2 is statistically significant, you would keep beta 1 in the model. Or if you had an interaction term of x1, x2 and you found it to be statistically significant, you would keep both your x1 and x2 in the model. And then the problems of R squared. So we could use R squared with simple linear regression because it always had one predictor. But when you start adding more predictors, when you add more predictors, your R squared will always increase or stay the same on your training data. So R squared is not a good statistic to judge the performance of your trained data. In 3-3, we learned about validation set approaches. So the first one we learned about is validation set, where we essentially divide our data into nearly 2 equal parts. So this is going to display the lowest variance but the highest bias. And the perks, we only need to run one model. So it's the quickest runtime. Now k-fold cross-validation is going to be somewhere in the middle. So it's going to have mid-variance and mid-bias. We ultimately end up running k models. And then leave one cross-validation is going to have the highest variance but the lowest bias. And we're ultimately going to be running n, because k is going to be equal to n models. So validation set is going to have the quickest runtime, and k-fold is second quickest, and leave one cross-validation the third. Now linear regression has a special case where you can solve leave one out cross-validation, and ultimately only going to run one model. So have the same runtime as our validation set approach. That only applies for linear regression. Now in general, you want to use k-fold cross-validation with either k is equal to 5 or k is equal to 10. Subset selection. So subset selection allows us to start narrowing our predictor space. So the first one is best subset. So best subset, it's going to check every possible combination. But with that, it has the longest runtime and can't be used when p is greater than 30, or even more than 30 predictors. Now, forward selection is the only one that can be used when you have more predictors than the number of observations, or when you just have a lot of predictors. But it's not going to check every possible combination, so it might not arrive at the best model. Now, backward selection. So it can find when predictors have a positive effect on each other because it's working backwards. But just like forward selection, it doesn't check every possible combination. So it might not arrive at the best model. So when we're using our subset selection, we can use either something like R squared or sum squared error to compare models that have the same number of predictors. So if a model has 2 predictors, we can find the best R squared and best sum squared error model. But to compare models with different number of predictors, so the best model with 1 predictor and the best model with 2 predictors, we can use different statistics that have a weighted element to them that add a penalty for when you add extra predictors. And our options for this are either going to be our Mallow CP, our AIC, our BIC, or our adjusted R squared. So Mallow CP and AIC will arrive at the same solution, and then BIC is going to weight predictors more heavily. So usually you're going to end up with less predictors from your BIC model than if you were to use AIC or Mallow CP as your statistic. And then adjusted R squared, just like R squared, you want to achieve a higher value is better. But it doesn't have the same interpretation as your general R squared, as the amount proportion of variance explained. And these 3 statistics, lower values are better. And then instead of using these 4 statistics, you could also just use cross-validation to compare your models that had different number of predictors. So if you had model 1, model 2, model 0, and then if you just use cross-validation and see which one produced the lowest either mean squared error or squared, and then you could choose that model. But of course, the runtime would be much more for that than if you were to just use a statistic like one of these 4. Okay. The assumptions of linear regression. So the first one is that there's a linear relationship between the response and predictors. So how would you find this? Either with residual plots or scatter plots. So the problems it causes when it exists is that you can't trust your coefficients, standard errors, or your predictions. And then how would you fix this? So you can add either polynomial terms or some type of transformation to your independent variables. Second assumption is that you have uncorrelated error terms. So how would you find? You'd find it in your residual plots. The problems it can cause is you end up with lower standard errors than you should. And this makes it more likely to keep bad predictors. And then your solution is it probably needs some type of time series element added. And we will cover that next chapter. The third assumption of linear regression is that you have constant variance of your error terms. So this can be found in your residual plot. Problems is you can't trust your standard errors. And your solution is going to be to apply a transformation to your dependent variable, such as the log of y or the square root of y. Fourth assumption of linear regression is that you have no outliers. So how do you find? So either in scatter plots, residual plots, or algebraically. For algebraically, it would be 3 standard deviations. The residual would be 3 standard deviations away from the mean, or from 0. And the problems it can cause, so it can inflate your test statistics, like your mean squared error would be much higher than it should be, and your r squared would be much lower than it should be. Solutions, so you can try to find a predictor that explains the observation. Or if it's a possible data entry error, just drop that observation. The fifth assumption of linear regression is that you have no high leverage points or unusual x values. So how do you find? So the same way you would find with an outlier. It's either in your residual plots, your scatter plots, or algebraically. So the problems that can cause. So it can change your coefficient estimates. And possible solutions would just be remove it from the model. Might be from the wrong sample space. And the final assumption of linear regression is a no multicollinearity. So you'd find it in linear regression using variance inflation factors. So a variance inflation factor above 5 is cause for concern. And a variance inflation factor above 10, you have a problem. So the problems that it causes is it increases your standard errors. And this makes it more likely to drop predictors. So the solution would just be to remove one of the highly correlated variables. In 3-5, we covered standardization. So if we center a variable, we set the mean to 0. If we scale, we set the standard deviation to 1. And then if we standardize, we just set the mean to 0 and the standard deviation to 1. Now we didn't cover normalization, but if you normalize a variable, essentially you're setting on a scale from 0 to 1, where 0 value would be the min observation from that variable, and 1 would be the max. And this is common in neural networks. Now, if we wanted to create either a polynomial term or an interaction term in our linear regression model, then we should center our predictors first in order to avoid multicollinearity. And then if we wanted to compare our predictors on a similar scale, so say one was in thousands and one was in tens, then we can standardize both our predictors and our dependent variable. And this will allow us to say, with a 1 standard deviation in x1, we can expect a 0.5 standard deviation increase in y. Or with a 1 standard deviation increase in x2, we can expect a 0.2 standard deviation decrease in y. Now when we standardize our predictors, whether we center, scale, or standardize them, we will still get the same predictions, the same standard errors, and the same coefficient estimates. We just have to remember to apply the transformations also to the observations that we add. Now if instead we were to apply a transformation, so here we're taking the natural log of y, which we would use to address multicollinearity, now our predictions are going to change. Our coefficient estimates are going to change. And our standard errors change. And essentially, if we were to make a prediction with this side of the model, we would get our prediction in terms of the natural log of y. So if we wanted to convert back to its regular units, we would just take the exponent of this value to get our new prediction. In the last section, we learned about ridge and lasso, which are two shrinkage methods. So instead of using subset selection, we could use ridge and lasso. So both of them have a tune-in parameter lambda, where as we increase the value of lambda, the flexibility of our model decreases. So with the flexibility decreasing, this means we'll have a higher train error. So we have a higher train sum of squared errors. We're going to have higher bias and lower variance. So the goal of increasing lambda is that we want our variance to decrease faster than our bias increases. So with ridge, our goal is to minimize the sum of squared error plus the summation of our coefficient estimates squared. With lasso, our goal is to minimize the sum of squared error plus the summation of our absolute value of our beta coefficients. And then both of these should have the tune-in parameter lambda, which affects the weight of this side of the equation. Now, ridge, it does well when you have similar coefficient estimates. So for instance, you have like 10 beta 1 plus 15 beta 2 plus 7 beta 3. And then lasso does well when you have a lot, or say some really high coefficient estimates. So we can say 100 beta 1 plus 200 beta 2, and then some really low coefficient estimates. Because essentially with lasso, you can perform feature selection. So as you increase the value of lambda, these values will shrink, and some of them will become exactly 0. So if you perform lasso regression, and this was your original linear regression equation, then it's likely that these two parameter estimates will get canceled out, and you would just be left with shrunken parameter estimates of these two. Meanwhile, with ridge, your coefficient estimates will approach 0, but they'll never actually equal 0. So if we just kept up in our lambda parameter, these values will just get smaller and smaller, but they'll never actually hit 0. So lasso is the advantage of also performing feature selection. So that wraps up linear regression. So now we're going to cover KNN real quick. So KNN can be used for both regression and classification. So KNN doesn't build a model at all. It's a memory-based approach. So it's going to choose the closest observations when you try to make a prediction based off Euclidean distance. Now, if you want to run a KNN algorithm, the first thing you should do is standardize your predictors if they're not already on the same scale. And then KNN has a tuning parameter k. So as k increases, we can expect the bias to increase, but the variance to decrease. So as k increases, our flexibility decreases. As k decreases, our flexibility increases. If we want to choose the appropriate value of k, we can use cross-validation. You can either use something like k is equal to 5 or k is equal to 10 for a cross-validation estimate. And then if we want to choose the appropriate value k, we'd enter different k values in. So we could say k is equal to 1, 2, up to say 20. And then whichever one produces either the smallest mean squared error, if it's for regression, or the highest accuracy, if it's for classification, you would choose as your final tuning parameter estimate. Now with k, you need a lot of observations. So because it doesn't have any of those assumptions like linear regression had, it's highly flexible. So essentially you need a lot of observations to be able to overcome the high variance. So that wraps up the review. Hopefully at this point you're feeling pretty confident about linear regression in KNN, and I'll see you next time for time series.